Hello and welcome everyone, wherever you are in the world, and welcome to our fourth in the series of our DOSI 10-year anniversary webinar series. Please be aware that we're going to be recording this webinar for future dissemination via our network. It's going to be available on the DOSI website and also via our DOSI YouTube channel for those who can't join us today and for those who might want to watch it again in the future. My name is Dr. Maria Baker. I'm from the School of Ocean and Earth Sciences at the University of Southampton, and I'm the Executive Director of the Deep Ocean Stewardship Initiative. So today we're delighted to bring you some leading voices on the topic of decarbonisation in the deep ocean. And they are namely Dr. Maria Emilia Bravo from the University of Buenos Aires in Argentina, Dr. Erik Cordes from Temple University in the USA, Dr. Bruce Applegate from Scripps Institution of Oceanography in the USA, and we also have a bonus speaker who's our DOSI Director of Communications, Brandon Gertz from the University of California, San Diego. We're going to kick off then proceedings with Emilia. And Dr. Maria Emilia Bravo is a research scientist at the National Council for Scientific and Technical Research, CONICET, the University of Buenos Aires in Argentina. And she's a member of the GeoFlamma team, I think I've said that right, dedicated to marine geophysics. Alongside Erik Cordes, who's also on this panel, and Daniel Jones from the NOC in the UK, Dr. Bravo has been a volunteer co-leader of the DOSI Offshore Energy Working Group since 2022. Holding a PhD in biology from the National University of the South in Argentina, Dr. Bravo specialises in discovering and describing coal seeps and their effects on benthic communities in Argentinian waters. So over to you, Emilia, please, to introduce the subject of your presentation. If you could share your slides, please.
Okay, so I will talk about some pathways and challenges of the decarbonization of oil and gas industry. Decarbonization or reduction of carbon and gas emissions into the atmosphere is part of a series of international policies and agreements that since 1988, with the creation of IPCC, have been seeking solutions to climate change. In line with that, energy production accounts for approximately 3/4 of the carbon gas emissions, mainly from the combustion of fossil fuels, which means that carbon emissions generated by fossil fuels directly affect the realization of global carbon neutral targets. But what happened with the oil and gas industry is currently expanding, and this is supposed to be related with the increase in global consumption of oil and gas. So apparently there is a growing demand for oil and gas, and this is growing very quickly. And here you can see some plots that indicate some of the areas where the oil and gas reserves are still available for production, and highlighted is the role of South and Central America to the top and right of the slide. You can see that South and Central America have more availability of oil than what was used so far, and the contrary is the case of Europe and North America. And the same in terms of the production to consumption ratio, that demonstrate that some regions are importing oil and gas while others are exporting oil and gas. And in any way, as a result, and advocated to the deep ocean specifically, this means that the oil and gas is expanding, and especially in deep waters, and especially in the global south. And here are some examples of exploratory blocks in the offshore. Here are some examples in Colombia, and some of these are currently in exploration, but also there are blocks that are currently being exploited in all cases. So here Also examples from Trinidad and Tobago, Guyana, Suriname, French Guiana, also Brazil, Uruguay, Argentina. And in Argentina this year, we'll probably have more blocks for exploration. Here are some examples from Africa. Here you can see blocks in South Africa, Nigeria, Namibia, Lebanon. These are cases of Australia, New Zealand, Malaysia, etc. So how we can reach decarbonization in oil and gas? There are a series of pathways, and for me, the first and most important is the change of the energy source to low carbon emission sources. Currently, we are using mostly fossil fuels, especially oil and gas is currently representing 50% of the global energy consumption sources. And in a net zero emission scenario by 2050, this should be reduced, but also replaced by renewable energies. And this will be expanded by Erik in the next presentation. The second pathway for decarbonization would be to decarbonize the current and future operations of oil and gas, because they account for around 15% of total energy-related emissions only in 2022, and the use of that oil and gas that was produced was related with 40% of emissions. So to decarbonize oil and gas operations, the International Energy Agency proposes a series of measures that are ready to use and cost-effective measures, and this could be key enablers for reaching the net zero scenario by 2050. But for that, the yearly target is by 2030. So that's why the International Energy Agency is talking about 2030 targets of reducing by half the emissions intensity. These measures include tackling methane emissions, eliminating all non-emergency flaring, electrifying upstream facilities with low-emission electricity, equipping oil and gas processes with carbon capture, utilization, and storage technologies, and expanding the use of hydrogen from low-emission electrolysis in refineries. Sorry. So this, together with the reduction in the demand, will give a reduction by half of the emissions related with operations of oil and gas. What about the feasibility of the implementation of these measures? The investment needed for applying the implementation of all of these measures together globally in oil and gas operations is estimated in $600 billion. This can look like a huge amount of money, but it represents only 15% of the income that oil and gas industry received in 2022 only. But additionally, the oil and gas industry would increase systemic efficiency and get additional income streams from the implementation of these measures. Another pathway to reach the net zero targets are the agreements. And here I added an example of the COP28 in the Oil and Gas Decarbonization Charter, because it has, this was a case where oil and gas companies represented largely the global oil production and the national oil companies. So over 40% of global oil production was represented by the signatories, but also 60% of the national oil companies were represented. So these companies have been committed through this charter to net zero operations by 2050, ending routine flaring by 2030, and near zero upstream methane emissions. But also they committed to invest in renewables, low carbon fuels, and negative emissions technologies, increasing transparency, alignment with broader industry best practices to accelerate decarbonization, and also to reduce energy poverty and provide secure and affordable energy to support the development of all economies. Some of the main challenges when we talk about decarbonization of the oil and gas industry include that the oil and gas were key for industrial revolution and plays a decisive role in all aspects of economic and social development. And this means that the removal of fossil fuels require completely restructuring the basis of all industrial economies, that is the energy, basically. Oil and gas industry is the single industry concentrating most power and influence on Earth. But at the same time, companies work separately. They have different starting points, different national contexts, and different stakeholders. So the climate change strategies are decentralized and disparate, and this reduces the speed of implementation of these strategies. Some final remarks. Some companies have to date announced a target to reduce emissions, but only a small fraction achieved the net zero emission scenario that was the one recommended by the International Energy Agency. But also, most companies are planning to use offsets to achieve their targets. Companies need to move faster in the reduction of emissions, building partnerships among companies, as well as public confidence in actions being taken. Thank you.
Thank you very much indeed, Emilia, for that wonderful presentation, enlightening talk. Up next, we have Dr. Erik Cordes, who is a full professor and vice chair of the Department of Biology at Temple University in Philadelphia in the USA. Dr. Cordes has worked on the ecology of the deep sea for over 30 years with over 100 publications. I'm glad I got that the right way around. From over 30 research cruises to the Atlantic, Caribbean, Gulf of Mexico, and Pacific Ocean. He is a self-described ocean explorer and ecological oceanographer whose research is focused on high biomass seascapes and their conservation. Dr. Cordes received his Masters of Science from Moss Landing Marine Labs, his PhD from Penn State University, and was a postdoctoral fellow at Harvard University before moving to Temple. So Erik, over to you with your presentation, please.
Thank you, Maria. And thank you, Emilia, for that wonderful setup of sort of the problem that we face moving forward with offshore energy and trying to decarbonize this industry. Obviously, to achieve some of the UN Sustainable Development Goals, particularly those in the oceans, it is necessary for us to move forward pretty quickly with this change in where our energy comes from and really the fundamental change in how this industry operates. And Emilia laid out the scenario for how that's beginning to happen very well. I want to look at a few of the details of how that might happen on the ground. And one of the major things that we're dealing with is looking at the offshore infrastructure. These are all of the production platforms in the Gulf of Mexico right now. There's about 1,300 offshore. This is in deeper water depths over about 50 meters. This doesn't include many additional platforms that are in shallow waters. And in sort of the global north in a lot of these areas, you can see in the UK, in the US, Norway and Brazil in particular, but across the world, one of the major things that's going on now is decommissioning, which involves, in general, removal of a lot of these structures. There are some movements underway to keep them there as through Rigs to Reefs program to increase fish abundance. And I'm not going to get into that in too much detail, but happy to talk about that another time. But the fact is that this is really, decommissioning is now being viewed as a growing industry, and there are a lot of different groups that are sort of positioning themselves to take advantage of the amount of money that's going to be spent to remove these platforms. But there is also the possibility for reuse. This is sort of a fanciful project, but one that is underway offshore Saudi Arabia. This is called the Rig, and this is the actual plan right now, the design for what this rig is going to look like. Basically a giant offshore hotel and amusement park. Now, I'm certainly not suggesting that that's what we do with all of these, but it is an intriguing idea. There are a lot of other things that we could do with this existing infrastructure offshore, and one of them is to turn them into energy generating platforms, but using other technologies. So that could include solar and wind. It can include OTEC, which is ocean thermal energy conversion, which essentially takes advantage of the thermal gradients from shallow to deep water to generate energy. And a lot of these renewable energy technologies can be used for hydrolysis, which Emilia also mentioned, to generate hydrogen, which Bruce will be talking about in just a second. And that hydrogen can be pumped back onto land using existing pipelines. And so there's a lot of effort and research and development going into using the existing platforms, the existing offshore infrastructure, but for different purposes. Another one of those is potentially carbon capture and storage, where you would turn the pipeline around and you would capture carbon on land, or potentially bring it out to these platforms and then pipe it back into the reservoirs where the oil and gas was originally removed. And the image of the platform up there is one in the North Sea, where they're actually testing this technology now and trying to put this into production. By far the biggest and the energy sector with the most potential, and the one that's moving forward the quickest, is offshore wind. There are lots of projections for where offshore wind is most viable, where those winds could be harvested. This is the one for the United States. This is being publicly supported in a lot of ways, and in some cases not being supported for various reasons, a lot of which personally I don't think make a ton of sense. They're more related to not having this in your backyard kind of arguments. But anyway, this is a very active area, and there's a lot of discussion about how this should move forward. This is the global map of wind density potential, so you can imagine where these are moving forward quickest. And a lot of these areas do overlap with significant areas of oil production, particularly in the North Sea, and you can see in the Southwest Pacific, where a lot of these platforms, this existing infrastructure, could be turned into offshore wind. This is growing very, very quickly, particularly in the Asia Pacific sector. China's really leading the way with developing offshore wind right now, in terms of installed capacity and moving forward into the future, although this is Europe, the Middle East, and Africa are not far behind, and the US is lagging, the Americas in general lagging a little bit in this, but still increasing pretty dramatically. This is a view of just some of the wind projects that are under development. A few of these are in operation, but the vast majority are under development around the United States. These don't come with zero risk. This is still a fairly challenging environment to work in, as a lot of people in this audience appreciate. There are a lot of different designs for how these structures are going to be put into place, and there's increasing effort looking into the potential environmental impacts of these. Like I said, they don't come without impact. There are bird strikes, although I like to point out that it's roughly 2 orders of magnitude more birds are killed every year by domestic and feral cats than are killed by even the potential for offshore wind development. So you might want to look in your own house at your cat if you're thinking about whether offshore wind is a good idea or not, and using the bird strikes as an argument. But this study that was just released, actually just a few days ago by the National Academy of Science in the US, was looking at impacts from one example off Nantucket, and they were looking a lot at the impacts in the midwater in terms of the physical oceanography and the potential for zooplankton distribution, nutrient distribution that can have trophic effects up trophic levels to the, in this case, the right whales in the Atlantic. But there is a lot of biomass on these structures. This ends up on the seafloor. You can have some eutrophication. You can lower oxygen. None of these impacts, I would point out, are anything remotely near the issues with burning fossil fuels and the potential for oil spills. There's no such thing as a wind spill. And so while we do have to think about these impacts, this is obviously something that should be going forward and something that is going to globally reduce our impact overall on the environment. So that's it, and happy to take any questions afterwards.
Thanks very much, Erik. Another great talk, and lots to think about there. We are now going to move on to our third speaker for today. Dr. Bruce Applegate is Associate Director of Scripps Institution of Oceanography at the University of California, San Diego, where he has executive responsibility for the management of the Scripps fleet of research vessels and the scientific capabilities aboard them. This includes global logistical activities conducted from the Scripps home port at Nimitz Marine Facility in San Diego Bay, as well as the vessel recapitalization efforts that he'll speak to today. Dr. Applegate holds a PhD in marine geology and geophysics from the University of Hawaii and is currently the chair-elect to the University National Oceanographic Laboratory System. So I'll now hand over to you, Bruce, for your presentation, please. If you could upload your slides. Wonderful.
Great. Thanks for that very nice introduction. It's a pleasure to be here today. I'm going to switch gears a little bit and talk about efforts that we have underway at Scripps Institution of Oceanography to really sort of walk the walk. We've been talking about decarbonization in lots of different ways for a long time, but we're in a really unique position at Scripps in that we're about to recapitalize one of our ships. This is a slide showing the 3 ships in the Scripps fleet. We have ships of various sizes, all ocean-going vessels. And the one on the left is Robert Gordon Sproul, which is a 42-year-old ship. And if you know about ships, you know that's very old. And it's time to replace Robert Gordon Sproul. And when we started thinking about how to do that, we thought about our own role in understanding and protecting the environment we want to study. And we thought about the impacts that Robert Gordon Sproul and other ships have on the ocean environment and the human environment on shore as well. And we started looking at the emissions impacts of the ships that we operate. And one of the things that we learned is the emissions that happen at sea don't stay at sea. This is a map showing the Southern California area, which is sort of the main stomping grounds of our small ships. And you can see offshore the Los Angeles basin here. The top slide shows sort of what the baseline condition would be if there were no ships included in an emissions picture. But if you add ship emissions back in, you can see on the bottom that the darker shades show where those emissions occur. In the bottom left, it's NO2. The bottom right, it's diesel particulate matter. It doesn't matter what criteria emission you study. These patterns all look the same. And you can see that the onshore flow brings all those pollutants ashore where we live. And we know that these impact human health, and that's bad. So we didn't want any part of that at Scripps. But also, we didn't want any part of the contribution to greenhouse gases in the atmosphere. And if you look at the Keeling curve and sort of the history of the Keeling curve, which of course got its start at Scripps, and you superimpose on that the introduction of new research vessels in the U.S. academic research fleet, of which we're a part, those are the vertical red lines shown here. And a few of the ships are pointed out just above the Keeling curve there along the top. Each of these vessels uses diesel as its fuel, and each of these pumps CO2 and criteria emissions into the atmosphere. And our ships at Scripps alone use more than 1.5 million gallons of diesel fuel per year, which equates to almost 36 million pounds of CO2 per year by our ships. And so we really don't want to be part of the problem that we're studying. We want to be part of the solution. And if you look more broadly in the maritime industry, so we at Scripps are a very small player, and research vessels themselves are a very small segment of the overall global shipping industry. But if you look at the whole shipping industry, and if you considered just emissions as the metric for how big something is, ships would be the 6th biggest country in the world by their CO2 emissions. And the graph on the right, of course, shows that the rates of production of CO2 just continue to increase as global shipping increases. So we need to bend the curve back down. And just recently, the International Maritime Organization has recognized that and has begun to set targets. There's a preliminary target at 2030 and then ultimate targets at 2050 to try to achieve net zero by 2050. And some ideas about how to do that. But the problem is that like other heavy industry sectors, the maritime industry is super hard to decarbonize. And why? It's because we're addicted to the convenience of fossil fuels. It's very energy dense. It's in the case of diesel, it's liquid at room temperature and very well known and used. So it's cheap and easy. And so solutions require outside the box thinking and different approaches. And that's what we began doing when we started thinking about recapitalizing our little ship, Robert Gordon Sproul. So in about 2016, we partnered with folks at Sandia National Labs in the United States, who were sort of federally supported hydrogen experts in the United States, and asked the question, is it possible to build a research vessel that's entirely operated without fossil fuels? So we completed a feasibility study with Sandia, our colleagues there, supported by the U.S. Maritime Administration. And the answer was yes. Not only was it technically feasible using commercial off-the-shelf products, but as a ship operator, I was interested in other aspects. Could we source the fuel? Is there enough fuel? Does the regulatory framework exist where we could actually build a ship and operate a ship within the flag state and our classification society? We asked all those questions, and the answer was yes, we could. So that was very promising. Unfortunately, the platform that we were considering was bigger than what we need now at Scripps. So we rescoped, and we thought, well, what if you have a smaller vessel? Could you achieve something similar with a smaller vessel? And with variations, the answer is again yes. And the variations in this case are that it depends on sort of the size of the vessel that you're building and the range that you require as to whether you can achieve zero emissions using hydrogen, which I should say hydrogen was the fuel that we selected in our earlier study, because in California, we are part of a very robust hydrogen economy here. So we know that hydrogen is readily available. We can get it at scale. And so that's the fuel that we looked at. In maritime, there's 2 other fuels that are low carbon that are being considered as shipping fuels as well. One of them is ammonia, which comes with a whole series of its own risks. The other is methanol. But both of those fuels are considered derivatives of hydrogen because they can be synthesized from hydrogen feedstock. And the great thing about hydrogen, of course, is that you can make hydrogen entirely without fossil fuels using electricity that's sourced from solar, wind, other non-carbon sources. And in California, supported by the Department of Energy, we've just established a hydrogen hub here, and we have a plan for creating an even more robust and vertically integrated hydrogen ecosystem with the hope that green hydrogen, that is zero carbon hydrogen, can be produced in California, not just sustainably, but economically, so that in 5-8 years, it just makes the most sense to use hydrogen as a fuel. So for those of you that go to sea, just a little eye candy about what a ship like this looks like. This is a It's a 50-meter ship, so it's a little bit bigger than Robert Gordon Sproul, which is 125 feet. So this is about 165 feet vessel. And our intention was to do a replace in kind so that the vessel was supposed to be the same size and the same footprint, but we added 20 feet in length. And that's because the vessel that we've designed, you can see there's a hydrogen tank. This will be a liquid hydrogen fueled vessel, and it'll use 6 fuel cells to provide the electrical power that'll provide the propulsion power as well as the hotel load on the vessel. It turns out that the hydrogen tank that we can get on board can only carry enough hydrogen so that we can conduct about 75% of our missions zero emission fossil free. So it's that other 25% that keeps me up at night. And how do we get rid of that? Well, so what we're doing with this design, this vessel design, is we've included tankage in it so that we can eventually use methanol as an alternative fuel, so that when you're on missions that require more range than you can achieve on hydrogen alone, you can switch over to using methanol. The reason we're not doing this initially with the vessel, initially this alternative fuel will be diesel fuel. The reason we're doing that is because currently the technology for converting that methanol to electricity that we need doesn't exist to fit inside the small ship that we're building. So we expect that, because we're talking to the manufacturers of this equipment, to be available in the next 5 years or so. So we have a plan to repower the vessel and eliminate diesel from the vessel entirely by probably 2031. Quick schedule. We're underway to build this vessel now. We have a project construction team. We're about to issue a solicitation to compete for shipyards, and we hope to have it on the water in 27 and operational for science by 2028. And I'll leave you with this slide. Basically, there's a rendering in the top right that shows what this will look like offshore La Jolla when we're operational. And one of the great things about hydrogen is it comes with so many benefits. Talk about you can't have a wind spill. Well, if you have a hydrogen spill, a liquid hydrogen spill, liquid hydrogen flashes to vapor phase very quickly. And once it's a vapor, it evacuates itself to space at 30 miles an hour. So we calculated that if you crack the entire tank open on the deck like an egg, spilled it all of it would be gone in less than 30 seconds on its way to space, where it actually leaves the planet eventually. And before you can even call the Coast Guard that you've got an oil spill. And you wouldn't, you'd have a fuel spill and it'd be gone. So to us, there's just a ton of benefits from moving away from fossil fuels for us into hydrogen, but we'll also be testing alternative low carbon fuels as well. And this is going to be the first ocean going liquid hydrogen vessel in the world. There's a couple other that work inshore waters, but we're very excited about this, and we're hoping that everything that we learn we can pass on to the rest of the maritime industry so others can begin to decarbonize other kinds of ships as well. And happy to take questions afterwards, but I'll leave it there for now.
Thank you very much indeed, Bruce, and I can hear your the excitement in your voice around this project, which is indeed very exciting for the future. Okay, so fine. I've seen a couple of questions come in, which is great. Do keep those coming. While we listen to our final speaker, our bonus presentation comes today from Brandon Gertz. He is DOSI's Director of Communications, responsible for coordinating DOSI's outreach to policymakers and supporting our network of experts, our vast network of experts of over 3,000 people now in total from 115 countries, so he's busy. He holds a master's degree in ocean policy from Duke University, and I'm now going to hand over to Brandon to explain about his contribution to this meeting.
So thank you, Maria, and thank you everyone for joining us today. Our presenters so far have touched on a range of industries involved in decarbonizing the deep ocean. But one thing that we haven't talked about so far is the fishing industry. And the United Nations Conference on Trade and Development just released a report on energy transition of fishing fleets that the organizers of this webinar wanted to make sure that we mentioned. So I'm going to cover the basics here. As a disclaimer, I am not a fisheries scientist, and I did not help write this report. So while I will summarize the main points, I highly recommend reading the report yourself if you would like more details. The key items this report discusses are, first of all, the carbon emissions we see coming from fisheries, actions that are being taken to reduce those emissions now, equity concerns in those emissions and the reductions that come with them, and then also suggestions for future steps to improve decarbonization and energy transition of fishing fleets. So it starts out by covering the problem, the challenge of carbon emissions in fisheries. It points out that fisheries currently account for somewhere between 0.1 and 0.5% of global carbon emissions, and that's coming from both industrial fleets and smaller scale artisanal fishing. That total amount comes up to about 4% of the carbon emissions created by food production. And the issue with identifying exactly what the numbers are is generally due to the data gaps, the unfortunate lack of information we have regarding many aspects of fishing and emissions connected to fishing. They also make sure to point out, the authors of this report, that while these emissions exist, they exist because fishing is an industry that is crucial for global food security and livelihoods. So what is being done about these fishery emissions? One of the key points the report mentions is nationally determined contributions from the Paris Agreement, where countries are obligated to define their own steps for reducing emissions. Some of those contributions, those statements mention fishing, others still do not. 3 of the top 10 countries that export fishery products, for example, do not mention fisheries in their nationally determined contributions yet. In 2022, there was a World Trade Organization fisheries subsidies agreement to try to limit subsidies related to fisheries to help counter overfishing. That hasn't gone into force yet, but it's been agreed. There has been exploration of alternative fuels, gear, and practices of fishing. So electrical motors, biogas motors, identification of where to fish that will help lower effort and therefore hopefully emissions. And yet, despite these efforts, work on lowering carbon emissions is still slower than work on the same process in the shipping industry. The fisheries have not kept up to the extent that the shipping industry has progressed. There are not usually global targets for emissions reduction goals relating to fisheries, according to the report. And the report came up with several categories of suggestions to help further the cause of carbon reductions in fisheries. Some from an economic perspective include designing comprehensive mitigation and adaptation plans for countries in the fisheries sector to improve their situation domestically and fishing in international waters. Also, improving that data access, reducing the data gap, establishing a global system for collecting, understanding, monitoring, and reporting that fishery emissions data. They also call for increasing exploration of sustainable fuel options and related technologies. From a trade perspective, the report suggests phasing out fossil fuel-based fisheries subsidies, adding carbon footprint criteria to voluntary standards that countries and organizations can take, or to, for example, consumer sustainability guides so that consumers can understand the carbon footprint of where their fisheries products, their seafood, is coming from. Then also improving sustainable port infrastructure and access to affordable financing, especially for developing countries, so that as better methods of fishery sustainability become available, developing countries are able to take advantage of them with proper infrastructure. Environmentally, the report calls for an agreement on a global emissions reduction goal for fishing fleets, updating those nationally determined contributions so that they do include fisheries targets and scale up general mitigation commitments, and then supporting effective stock and ecosystem management so that fisheries don't need to require so much effort and potentially emitting activities in the first place. And while doing that, there are a couple of social considerations that they recommend taking into account, ensuring that any of the changes above promote a just energy transition, and making sure that as the process continues, minimum working conditions and safety in the fisheries sector are ensured. So that is a very brief overview of the contents of this report. If you want to read the report for yourself, there is a QR code here that you can use to link straight to it. Otherwise, you can just search up the name, or when the recording of this presentation comes out, we will make sure to link it in the description. Thank you very much. Back to you, Maria.
Thanks very much, Brandon. A shame I can't see you, but you did wonderful at that presentation. Thank you. I have been one of these people who hasn't got around to reading that report yet, so it was great to have that summary. Thank you very much to our speakers. It's been fascinating, and I'm sure there'll probably be more questions coming your way to all of you post-webinar. So thank you very much. It just remains for me to say thank you very much indeed for coming, and we look forward to you joining us next time.
Hello. I'm Brandon Gertz, DOSI's Director of Communications. Thank you for joining us for this webinar on decarbonization of the deep ocean. We will have more events in this anniversary webinar series coming up soon, so I hope we'll see you again. You can use the link in the description to keep an eye on what's coming next, and you can use this playlist to see all the webinars in this series so far. Thanks again. Take care.